Thank you, Jimmy, for giving me this opportunity. What I'm going to do is spend just a few minutes giving everybody a brief overview of what influx data is, what do we do in the space, why is time series so unique by itself, and what are the characteristics of building a time series system. And then after that, I'll pass on the ball to Robert to talk about the benchmarking exercise. So, this is essentially something that people in the community track. It's the ratings from DB engines, and DB engines has been, tracking this for the past year or so, and has been looking at different SQL and NoSQL database systems, all the way from object-oriented databases to time series databases. And for the past year or so, they have found out that time series platform database is the fastest growing NoSQL database platform. And I'll tell you when we talk about the use cases why, maybe what's driving all of these. Now, within the time series ranking platform, what the community, the users, and customers have rated based on the maturity of the product, based on how easy it is to use, based on the install base, and based on the development momentum. InfluxDB made it the clear leader for the past year or so. We are almost twice rated as the nearest competition. So on the right, you essentially see the time series database rankings. On the left, what you see is time series versus other relational and non-relational databases. So, just for the uninitiated, if you are really new to the open source community, Influx is a Go-driven project and a lot of contributors. We are up to 28,000 installs every month. Huge momentum. 8,465 GitHub stars, 235 contributors, and that's just for the database. There are many more contributors for the additional ecosystem surrounding Influx. Just a snapshot of who's using Influx, so that we get a fair idea. At this point, the question is who's not using Influx. There are thousands of startups as well as large enterprises who use Influx data in various forms, and they use it for building their solutions on a time series platform. So we talk about time series, but what realistically is time series data, right? There are different people who already know this, but just for folks who are coming in at the ground floor, right? On the left, you see time series data, which is specifically, ops data, CPU, disk, memory. On the right, you're seeing financial or fintech stock trading data, right? All of them actually are examples of time series because they have been plotted on an index. On one of the axes is time, and you are looking at them over a period of time to find out what happened in the past, what is happening now, and can you actually tell what's probably going to happen in the future, right? What is not time series data is something like these examples, where on the left you see a case of a classic graphing database, which shows relationships between nodes, as well as, each node essentially represents a collection of similar type of ideas. So if you're looking at examples on graphing databases, this would be Neo4j and others, which are hugely popular, but they are nothing to do with time series. On the right here is a segmentation score of user or student population, but based on how good they are in athletics versus how good they are in the grades, right? So this is a good segmentation or profile data, but it has nothing to do with time series. It could become something to do with time series when we look at this example. So on the left here, you see tweets based on hourly data, which is for hashtag royal baby arrived, right? So you're tracking it over time. So that becomes a time series data. But exactly the same data, if you start looking at it based on profile or geographical distribution, not trending over time, that's not time series data, right? So just to clear the concepts. So there are a lot of use cases. We try to bucket them into three major categories. But more and more users, right, are coming back and telling us they use time series, and in particular Influx platform, open source platform for IoT. because in IoT land, majority of all data is time series. There isn't many applications running on the sensor. All you can do is grab data, grab some metrics of these small tiny sensors. These could be Raspberry Pis in case of industrial IoT. These could be devices that you're putting in your factory floors, or even in case of commercial IoT, this could be devices you're putting in your homes and offices. And most of this data that is getting collected is essentially situational data, is health data, on-off data, tracking data, which is all happens to be time series. We are not running logs or any kind of agent-based technology there. Custom DevOps, too many people, too many tools, and folks have now started building end-to-end single pane of glass solutions using Influx data as a platform, and they are using the instrumentation agents and the ecosystem to grab data from different layers and not have to rely from out-of-box solutions. As well as from the real-time analytics world, you are seeing use cases around, real-time price comparison, deal engines. You're looking at presence services. You're looking at security and malware and phishing prevention services, and so on, right? So I'm not going to go into too much in depth. We did a webinar last week, and we can send you a link which goes in depth into these use cases. But just moving on, right? What kind of questions can you ask of time series data? So if you start looking with a lens of present and past, real world questions, for an operations guy, it can be as simple as, can I resolve an application outage before the customers start to complain? Absolutely, right? If I'm tracking it in real time, yes. If I'm a marketing guy, how long are visitors staying? And why do they drop off my e-commerce website, right? If I'm a security guy, my questions could be, can I detect malicious attacks or DDoS attacks in my network as it is happening? If you instrument all of these key parameters that you want to track upfront, believe me or not, all of these, you are interested to look at these events and parameters over a period of time, right? So data, by the way, happens to be most valuable when it is fresh. In today's agile world and customer-centric business world, where more and more businesses want to be real-time, they want to be tracking what the customer behavior is, and they want to run campaigns, right? Hey, somebody's lurking on my website, let me show him a discounting campaign, right? In these cases, you have to track on time, and you have to take real-time actions. Now, if you look at questions that you can start asking of the data to predict the future, that becomes really interesting. That's when things like predictive modeling and forecasting come in, right? So questions like, hey, can I project my revenue over the next 4 quarters, right? Or I have built an infrastructure, will it scale for Black Friday? Or if I optimize particular, I have a piping infrastructure in my industry. If I optimize particular flow rates over a period of time, will I essentially get better optimization and reduction in cost, right? So these questions are based on models, right? You gathered all these metrics, but then you have to work with some algorithms to get analytics and intelligence out of this data. So here's some patterns that you start recognizing in time series, right? There are many more. I'm not going to get into too many of them at this point of time, but if you're looking at randomly fluctuating patterns on horizontal axis, or if you are seeing secular positive patterns, which essentially on the right, top right, which shows trending data, or if you're looking at seasonal data, hey, you know what, quarter on quarter, the data says the same. Maybe it's customer growth, maybe it's the number of people who come to my website, maybe it's my operational capacity, or maybe it's my release cycle, right? So this is essentially seasonal data. Or if you're looking at long-term cyclic data, which kind of repeats over a number of years, so you can see a constant growing trend and similar fall-offs at cliffs, which are predefined on a longer-term basis in the cyclic patterns, right? So there are different patterns that you start emerging, and then you start doing intelligent analytics on them. However, to get to all this, right, let's start from the ground floor. what do you need? Like, why a time series database? Can't I do this with a general purpose database? Maybe, right? But here's characteristics of a time series database written by Baron Schwartz. So what he says is, 90% of the database workload has to be a high volume of high frequency writes. If you have a use case like that, maybe time series is the ideal platform for you. So you're looking at a lot of data coming in, and obviously you are querying as well. However, what also happens is, writes are typically appends. When you're creating a database like that, you are appending to existing measurements over time, right? So it's not that, new type of data or new series come in all the time. You are essentially appending values to already logged series, right? And these writes are done in a sequential order, right? You should be writing at a very high rate. Sometimes it's every second, sometimes it's every minute. You're not looking at running bad jobs once a day, right? Again, if you get constrained for resources, typically these are caused due to I/O issues, right? Now, there are different other characteristics, but to quickly come to the point, why is time series workload different? Why can't you handle it with different databases? So I would like to highlight three key data points. One is data lifecycle management. So you need to structure the data in such a way that you have high precision for a short period of time. Because if you're monitoring maybe for a day, a week, a month, you need high precision data. But you don't want to lose that data. You may want to downsample it, you may want to aggregate it for longer periods of time. In certain scientific projects, in certain fintech projects, you need to even retain the high precision data for even longer period of time. However, you need this flexibility, right, in terms of precision management, aggregation, as well as rolling up the data, right, which is not very easy to do in general purpose databases, right? And devices who, DBs who actually follow this, they have to devise schemes for cheaply throwing away large data sets, quickly summarizing them, and doing it at scale, right? So hey, if I am storing, let's say, one data point every 15 seconds, I need to be able to quickly summarize that data, let's say over a minute, when I start to aggregate it, and maybe throw away this data, and then keep moving averages for a minute, maybe for 5 years, right? And maybe I can be doing this at million writes a second. So I need to do it at a very large scale. And typically when you look over summarization, a computation of the data on so many time windows and creating summarizations and aggregations of the data, statistical aggregations of the data, is very, very hard to optimize for general purpose databases. And another, if you want to really take it further, you start building in-memory analytics on the databases. So if you have two time series data points coming in, and let's say you want to compute percentiles, or maybe you want to compute things like standard deviations, or maybe you want to compute these two time series metric and do some mathematical calculation, do a join, and then compute another value which is persisted back in the database as a streaming metric. So to maintain stream analytics on a regular time series basis is again difficult to do in general purpose databases. So these are some of the key bottlenecks, right? So just to talk about Influx, right? We essentially, when we designed it from the ground up, these were some of the key challenges that we were looking to solve, right? So other than the data lifecycle management, the high write speed, the query speed, simplistic SQL type language, we also have pre-built functions, right? So pre-built functions like mean, median, max, sum, standard deviation, spread, count, and so much. You have in-memory analytics called as continuous queries to create, your own custom metrics. And from an architectural layout, on the left, what you see is essentially our ingestion agents called as Telegraph, and it is a plugin ecosystem which has close to 85, 90 agents to gather data from logs, applications, databases, network, message queues, sensors, even hardware sensors, and containers, right? And all this data is written over a protocol called as the line protocol and fed into InfluxDB. And on InfluxDB, you can run in-memory analytics using continuous queries. But if you want to really run large volume ETL jobs or anomaly detection or even predictive modeling and machine learning, then you have a layer called as capacitor, which is essentially the analytics engine. And from the visualization perspective, we use Chronograph for the data exploration, but you can also use popular projects like Grafana to create dashboards in practically no time, right? And if you're really managing this at a much larger scale, looking at cross-geo replication and management clustering at a much larger scale, you have a product called as Enterprise, which lets you do all of that. So that being said, I just want to spend 1 minute on looking at the data schema itself or the data model. So the way Influx works as the time series platform is we have a set of measurements, tags, fields, and values, as well as a timestamp. And the combination of this actually makes a series, right? So if you start having a different measurement and tag, as well as fields, you can be creating more and more series. However, what we are really good at is supporting a very, very, very large number of series in millions, right? So for example, measurement here is temperature. Tags could be, device and building, right? And fields for that temperature could be internal and external. And the values that you're plotting is, 80 degrees is your internal and external temperature is 18 degrees. And the timestamps could go up to nanoseconds, right? We actually support up to nanosecond precision. So that's essentially a way, and this is the same data model that the line protocol follows, and that helps in very high optimization and compression ratios when we talk about dealing with this data in InfluxDB. Now, the bake-off for today, keeping all this background in mind, is Influx versus Cassandra. We all know that Influx is a time series specific platform, and Cassandra was designed as a more general purpose database. Obviously, it had its own niche, becoming a key value paired database, as well as you could also do columnar data on that. However, we did a benchmark, and you can see that Cassandra already was launched 5 years before Influx, right? So we use the latest versions of both the products. There was documentation that's linked here. Some key subtle differences. Obviously, Cassandra was written in Java. Influx is written in Go, which is a highly performant language. And the operating systems that it supports and the data access APIs that we ended up using are listed here. But at this point, I would try to hand over the discussion to Robert to talk in detail about the benchmarking. So I'm going to stop sharing and going to make Robert the presenter.
Hello, can you see my desktop, this presentation?
Yes, we can.
Great. Yeah, thanks for that intro, Shubhra. My name is Robert Winslow, and I'm an external contributor at Influx. And for the last few months, I've been working on benchmarking InfluxDB versus other solutions, and I've tried to come at it with a fair amount of rigor, as well as making these reports in a way that is relatable to people making decisions about whether or not to use Influx in the real world. So the key question we want to answer is InfluxDB faster than Cassandra for workloads you care about? And what I mean by this is, can we talk in the language of your problem domain? A lot of benchmarks are about highly technical sort of internal measurements of how databases perform. So we do that as well at Influx, but this is about mapping to sort of the use case. So before I get into the details, I want to go over some goals that we have for this. The first goal is we want to be realistic. As I mentioned a minute ago, we want to answer performance questions for real-world users. I personally love micro benchmarks. Every database seems to ship with them, but not as many explain the results in terms that customers can understand. In particular, for this, we looked at a very popular use case for Influx, which is the DevOps or developer operations use case. And we take an approach that seems to really model what people experience in the real world. With this, we want to be rigorous. When you're using systems that are very different from each other, for example, InfluxDB and Cassandra are very different from each other, you need to take a lot of effort or make a lot of effort to implement things in a way that it's correct and identical between the systems. And we have a number of ways that we achieve that, which we'll talk about later. Of course, it should be reproducible, like any good science experiment. And just like everything else at Influx, we open source this, and you can go check out all the benchmarking code. So in particular, Cassandra, as some of us probably already know, it operates at a different level of abstraction than Influx. It's more of a building block for making distributed data systems. Influx comes out of the box ready to handle time series data in a very performant manner. So when building this comparison system between Influx and Cassandra, we had to learn quite a bit about how to tune Cassandra and how to design our schema and some other things to show Cassandra in the best light. So concretely, what that meant for us was we talked to experts about how to build our Cassandra system. For example, we had to know ahead of time what Cassandra queries to support. And then along with that, we designed a Cassandra schema to fit our queries and the shape of our data. This is a kind of a core tenet of Cassandra design, is that you need to know ahead of time what your queries are going to be. And that's sort of this philosophy where by having a huge distributed database with Cassandra, you can sort of prepare ahead of time sort of what the query results are that you need to see. This is in contrast to Influx, which allows a large amount of ad hoc querying. The third point would be that, of course, Cassandra being a building block for building distributed data systems, you have to sort of decide ahead of time what sort of data flows are you going to have, how many points per minute or how many points per second, and you use that information that you know about your situation to pre-select a time granularity that would split data up between rows and tables. In contrast, Influx, there are no tunable parameters because we take care of that for you. And one of the biggest things, and I'll get to this later in the presentation, is we need to design both a smart client as well as sort of a high-level query to represent the time series query that we would make to Cassandra. The reason for this is that internally in Cassandra, in the schema that we have, the data that we're aggregating over, it exists in many places. And as we know, Cassandra does not handle arbitrary joins. And so we've developed a system that is in between the benchmarking client and the Cassandra server that fulfills those requests for us. So getting into the methodology, and if you saw the Elasticsearch presentation, some of this will look familiar to you. There are 5 phases, and these are all programs in the GitHub repo that you're welcome to go check out. So I'm just going to go through them one at a time. The first phase is we generate data. And so we have a DevOps data generator, and it creates a simulation that models a server fleet through time. We looked at, I learned a lot about Telegraph, which Shuber mentioned earlier, which is a metrics collection service. And they have many plugins, and so we chose a handful of those to model in the simulation. And the name of this program that generates the data for all the databases is called Bulk Data Gen. So again, with the rigor and the correctness aspects of this project, we pick a random seed ahead of time at the beginning of the benchmark. We generate data using that seed. And based on that seed, the entire data set is deterministic, so you can reproduce it. So I can tell you I have seed 1, 2, 3, and I use this many simulated server hosts, and that's all you need to replicate the data set. Concretely, we have 9 different measurements that we simulate. These are sort of just basic system metrics, CPU, disk, some other system things. And then to round it out, we have 3 applications, Nginx, Postgres, and Redis. Every machine that we simulate through time has a set of tags that are static. We pick these to be sort of, again, from the DevOps use case. And these are things like the architecture of the processor or the data center that it's in or the host name. And we had a little fun trying to make these realistic, so we use real AWS region and data center names. And so this is really where the simulation comes in. So for every measurement, again, CPU, RAM, disk, we have a number of values. And what I'm showing here is the CPU measurement. And this is straight from the Telegraph CPU plugin. Actually, I think it's default. I think it's part of the system plugin. And so most of these are simulated through time by what's called a random walk. So typically, you don't have just uniformly random CPU usage through time. You have kind of it'll go up a little bit, it'll go down a little bit, and it'll kind of walk around this graph from between 0 and 100%. So most of our metrics are simulated in 10-second intervals as a random walk through time. And then finally, the fourth component of any time series point, as Schubert pointed out, is the timestamp. So here we're utilizing the nanosecond precision available to us in Influx. And in lockstep, the simulation of these machines proceeds in 10-second epochs. So every 10 seconds, all machines and all of their measurements are enumerated, and the data is printed out to standard out. We were able to achieve nanosecond precision when storing this information in Cassandra because we used the 64-bit integer type. It's worth noting that their default timestamp type, I believe, gives about millisecond precision. So just to make it concrete, here's an example line from the line protocol format when using this generated data. The first field is the CPU measurement. Second one is the set of tags that identify this machine, virtual machine, application, and those are static through the lifetime of the simulation. And then the fields for the CPU metric there, those are the random walk values. And you can see they're all different, and I can't show you here. I'd love to have an animation, but it's a nice graph of all of these machines through time. And then finally, the timestamp. So the data generator is a simulation that is orthogonal to the database that you're going to be loading data into. Inside the data generator, there is one file for each database that converts a generic point into one that is for a given database. So for this benchmark, we used 2 different sort of drivers there, and that was one that would convert a point, an abstract point, into one for the InfluxDB line protocol, which is optimized for bulk writes, and then also one into Cassandra CQL. As a quick note, simulating data doesn't take that long to do, but certainly writing out the data to a file can take time, and importantly, it can take a variable amount of time. So the InfluxDB line protocol is very simple and straightforward to write out to a file. CQL is just a tiny bit more verbose. It doesn't matter in practice, but when writing out the data for the from the simulation, we want to be as fair as possible. So we generate the data ahead of time, save it to a file. That way we have no concerns about synchronously generating data and loading that same data. Concretely, we used a data set we're calling DevOps 1000. So this is a simulation of 1,000 machines in a data center over the course of a day. The notion here is that the 1,000 is what we call a scaling variable. So let's say that you double the size of your data center to 2,000 machines. With the simulation, you could just tick that number up to 2,000 and then see how these different databases perform. This is part of our effort to make the benchmarks immediately relatable to purchasing decisions by speaking in the language of the problem domain. So you'll notice that I've been speaking in the language of machines and DevOps and data centers, not in terms of the guts of database systems like Cassandra or Influx. Of course, we'll get into that, and that's the point of this presentation, but the benchmarks are supposed to be very relatable. So some things we had to think about at the data generation stage for Cassandra are, of course, knowing the schema ahead of time. So for simplicity's sake, we create different tables for each value type. So Influx supports a number of different field value types. So these are integers, 64-bit floating point values, and a few others. And so to mimic that in Cassandra, we created sort of a blessed key space with known ahead of time tables for each of these different types. Primary key, we use the series name combined with a timestamp. So the series name is the measurement, say CPU, and a set of tags that identify a machine. And the tags are sorted so that there are no incorrect writes to series that are not. Tags need to be canonicalized. And of course, it's always important how you choose a partition key. We chose the series name as the partition key. As a note, for longer durations of time series data, or rather longer spans of time, that time granularity question will come up that I mentioned earlier. And so the time granularity that we experimented with actually ended up being 24 hours, so it didn't apply to this test. But if you were to have were to use this in Cassandra, you would want to have the series name also have the time window. So it would be 24 hours, say. So it would be a series name every 24 hours, and you would merge those on the client through time when you're doing your aggregation queries. And finally, we chose to use compact storage. So just to summarize the data generation phase, we generate data from a simulation of servers. Every 10 seconds, each simulated host emits 100 field values across 9 measurement points. And we save it to a gzip file. And again, we decided the Cassandra data model ahead of time in accordance with best practices. So we generated data. Now we need to load it and benchmark write throughput. In the Unix tradition, we created a file, and now we're going to stream it through standard. The idea behind the benchmark, the writing benchmark, is that these programs read in items on standard in, and then the programs are responsible for sort of the parallelism involved or how big the batches are when doing bulk writes. And that lets us experiment with finding the best parameters for each database. And again, trying to make the sort of the benchmark parts of this pipeline as simple as possible so we get the best performance and sort of can make the best argument about the conclusions that we've made. So the data generator, it's fairly complicated, but it happens offline. The bulk writing benchmarker, it's pretty simple. We have 2 different programs, one for each database, and that's mainly due to the fact of these different protocols. And with both of them, you can tweak the size of how many points in a batch, and also how much parallelism do you want to use. In Cassandra, we use the Go library, GoCQL, which I had a really nice time using, and we chose to configure that with the Cassandra binary protocol v4. And of course, the code's online, so please go take a look at this. We did what we could to make the Cassandra bulk loader fast and fair, and after review from a number of friends of our company, I think we've achieved that, but more feedback, the better. The InfluxDB bulk load protocol is just kind of a straight HTTP post in a custom line format. So we use the Go fast HTTP library to achieve the best performance. So it's really just a parallel HTTP client. And here's an example, final output of the benchmarker for InfluxDB writing. It'll just show that how many lines per second you've achieved there at the end. It's one of 106,000 per second. And then some other information. Interestingly, of course, this is line-oriented in this example, so every line has multiple values. So this is approximately 1 million values a second in this small example. So on to phase 3 of 5, returning to the generation phase, but this time for queries. I'll get into that now. So similar to the simulation for the data point generator, we're going to generate queries ahead of time, do as much work as we can, well, reasonably, before running the query benchmarker, and then save them to a file, and that reduces overhead when running the benchmark. And also similar to the simulator that generates data to be loaded, the query generator logic is shared between the databases. And then within there are a few pieces of code that sort of render the generic queries into ones that are specific for each database. And this lets us sort of honestly reduce code maintenance burdens, but also you know, I can look at that and say, oh, that's correct, and most of the code is shared, and there are no special paths for each database. And again, similar to the previous phase, you know, I'm going to take a moment to talk about serialization overhead. So many benchmark suites generate and serialize queries at the same time as running the benchmarks. This is true actually in almost all micro benchmark programs that ship with databases. We don't do that, so we generate queries ahead of time, we save them to a file, and then we load them up separately during the benchmarking phase. So queries there are a few ways to think about them. For us, they fit sort of a template idea. So there's a query type or a few query types, for example. Show me the maximum CPU usage across these 4 or 8 or 12 or 16 hosts in the data center through the course of a day in 1-minute buckets, something like that. And so to fulfill that, you need parameters that it logically requires, such as the start time, the end time, maybe some of the selection criteria. And that's sort of what we would call a high-level query. And I'll get into how we turn those into low-level queries in a minute. But with Influx, that high-level query is actually what you would write in InfluxQL. It's extremely straightforward. For Cassandra, that's not the same story. Cassandra, we take a high-level query, and at runtime, we actually infer what we need to do with the database to fulfill that query. And that is using what we were calling the smart client, which I'll get into in a minute. Again, just some examples of queries. You can come up with an infinite number of these. For our benchmark, maybe Shubhra can speak to this, but we picked one that we felt was indicative of DevOps usage in the data center. So I actually found this fairly interesting. Cassandra is a powerful system, but it's pretty low level compared to Influx. So as I was mentioning a second ago, we had to design our own high-level query idea to represent the Cassandra operations we needed to perform. And in practice for us, those meant we were doing what's called a scatter-gather operation. So we take a high-level query, we use runtime data that we know about from the Cassandra database, and we combine them to come up with a simple query plan. And then that query plan is made up of a basket of actual Cassandra queries. We execute those queries, and we merge them on the client. And I'll come back to this later, but this is what we're setting up to do. And just for those of you who are not too familiar with Cassandra, this is sort of, it's okay. This is what you're meant to do. So Cassandra is a building block for building huge distributed systems. So we did have to invest a lot of effort up front to make it do what we needed to do. Here's an example of the high-level query for Cassandra before it's been put through the query planner that we wrote. and it is just sort of a codified representation of the query that I was talking about earlier, where you pick a measurement, you pick a field, a time window, a duration and group by, and some optional filters. And this is InfluxQL here. So this is the same query or a similar one. In the template format, you can see that we're using %s to indicate string substitution. And then in the second box here, we're substituting the actual concrete values. And this would be a good time to point out sort of where do those values come from. We have, just like with the data generator, the query generator is running a simulation through time, but its simulation is very simple. It's picking random values within the windows of time that we specify and random host names, and it's populating these queries. So one issue that we've had in previous benchmarks that we had to work around was that databases cache frequently requested results. And so to break that caching, we had to pick totally random time intervals. So here you can see it looks like it's about a 12-hour window, but it starts on a random second and minute boundary so that we don't accidentally use the database cache. And just as an overview, each Cassandra request is stored as a Go object protocol encoded type called an HL query or high-level query. Just for those of you who don't know, GOB is sort of Go's internal object serialization format, which made sense because all of our benchmarking tools are in Go. And then each Influx request is just an HTTP request that we also encode. On the benchmarking side, we're able to read about 700,000 requests per second on my local machine. We have plans to increase that for testing clusters. As I mentioned earlier, our query generator also is running simple simulation, and of course, it's also 100% reproducible. It takes a random seed and a scaling variable, such as DevOps 1000, to create the queries, and that makes it rigorous and reproducible. And when you're generating these queries, this is the sort of output you'll see for InfluxDB. It'll show you the random seed, and it'll show you how many points it made for what query types, and exactly the same for Cassandra. Source code's online. Please check it out. Give us feedback. And yeah, open a PR if you see something you'd like to change. So we're on to phase 4 of 5. We're finally going to run probably the most exciting part of this, which is the query benchmarking phase. So we've generated data, we've loaded data, we've generated queries, and now we're going to execute the queries. Just as previously, we're going to read that information in from standard in, and it'll be up to the query benchmarker at runtime, given user provided parameters, how much parallelism will be involved. For flexibility, we have 2 different query benchmarker programs, and their names are listed here. They both take the common parameters of the destination URL of the server and what level of parallelism to use. So as we talked a little bit about earlier, Cassandra is a very different system than Influx, and really where that comes through the most is in what the query benchmarker has to do to satisfy queries. So it's an extremely different program than the one for InfluxDB. And again, the way to think about that is that we have the client, which is going to be making requests to the system. And that's actually making requests to something that we call sort of a smart client, which sits in between between Cassandra and the query benchmarker. And the smart client aggregates the information, creates a query plan, and fulfills it. Finally, on the other side is actually Cassandra. So that middle piece, the smart client, it does a lot. So this is a benchmark, so we're able to take a little, this is not production level, but we did make it pretty, we did invest a lot of effort to make this realistic. So on startup, the query benchmarker, before it executes any queries, it does a scan of the key space that we're using in Cassandra, and it determines sort of table metadata, and it loads that up into the what we're calling the client-side index, which is effectively just a map of maps that keep track of what data is where. And this is mainly the point that you would really run into problems with in production, because you have a client and it needs to keep its knowledge of the Cassandra data store synchronized. We don't have to keep it synchronized because we know the data is not going to change during this benchmark. But in production, of course, the data will be changing, and so that is another problem that you would have to solve. So the benchmarker client, for each request, it reads in that GOB encoded item from standard in, and that is the high-level query or HL query that we talked about before. It uses the data that it has in the client-side index combined with the HL query to decide which concrete Cassandra queries will be needed to gather information to fulfill that query. Finally, it actually submits those queries to Cassandra and it merges them on the client. We had a previous strategy where we asked Cassandra to do some merging for us on the server before sending it back to us. That really increased latency, but it did decrease bandwidth. So what we have now is a fairly straightforward system where for every series, say CPU for virtual machine 5 in this data center, and a concrete field for a CPU would be, say, the usage for the user processes. We know ahead of time what time interval we want to aggregate over. And so for every series that fits sort of this filter, we grab the range of points that match, and we stream them to the client. And using a constant space aggregation algorithm, we stream these sort of windows of data points into the client. And then on the client, we merge them together. And so that is how we're able to perform some of the same basic things that InfluxDB gives us out of the box. This took a fair bit of engineering time. The amount of effort required to get sort of what I would call the hello world of time series databases going with Cassandra was huge. I understand that Cassandra is a very useful technology. I feel that the upfront cost in designing a system, at least in the time series use case for Cassandra, the upfront cost is very high. And I'm happy to talk more about this in the Q&A. And here's what it looks like when we're actually running the query benchmarker. There are a few lines here. This is actually for the same run. And what's happening is that we've broken down the time spent in query planning, which we note by QP here. So this is the type of query, a random set of 8 hosts from this data set in a 12-hour interval, aggregated over 1-minute buckets. And so this is how long it took overall on average. But this is how long it took to plan the queries on the client and scan through a lot of the client-side index. And that's not much time. That's about 500 microseconds. But that was not originally the case. When I first wrote this, that was taking a few milliseconds, and that was a bug that I had to stamp out. So there's just a lot of engineering that you've got to do when you use Cassandra like this. And for comparison, the InfluxDB benchmarker just submits the queries over HTTP. And just as previously, we use the fast HTTP library to achieve much better performance on the client. And this is the sample output from the Influx query benchmarker. And it just has the one line giving the average time per request. And that is, of course, because we're not doing any pre-processing or post-processing of the query results. So on to phase 5 of 5, and this is probably my favorite one because it shows the end-to-end validity of our whole benchmarking suite. So we're going to validate our results. We want to validate that the results we receive from each database are the same. So as I mentioned earlier, these systems can be very different. And of course, Influx is a startup. We like to move fast. And this is really the way that we can show that we did this correctly. So we have a couple of questions that we'd like to answer when talking about validation, and they help us identify that we were correct. So were the parameters and the points that we made in the simulation at the beginning, were they the same for both databases? Did we load them correctly? When we made queries, were those queries the same and the parameters the same? And then did the queries actually do the same thing in the databases? Did they return the same results? If the answer is yes to all of these questions, then we can be confident that our systems that are benchmarking two very different databases are achieving the same results. And so the best evidence of this is that we can actually compare using a diagnostic mode in the query benchmarker. We can compare the numerical results from each query. And so here, for comparison, is a simplified set of two responses. One is from a Cassandra query benchmarking run, and the other is from InfluxDB. And in this diagnostic mode from each query benchmarker, it will actually print the results that it receives from the database. In the first case for Cassandra, this is actually what the smart client has aggregated and decided as the answer. In the second case, it's coming exactly from InfluxDB. So if you just take a second to read the numbers here, you can see that they, if I did this right, they are the same values. So there's the same time window for both of these values. So it's 4:33 in the morning, both of them. And then actually the floating point values are the same within floating point tolerances. So just to emphasize, this really shows that the data in the databases is identical, and we're querying the data in the same way for each database. Of course, it's not perfect. Floating point being what it is, and different databases having different storage formats, there are small differences sometimes. I found that usually is after the third or fourth decimal point, though. Right now, we create a validation sort of text file for each run and go through it by hand to make sure that a couple hundred queries are identical. It'd be nice to validate it. One idea is, or to automatically validate it. One idea is that the simulation could actually know ahead of time what queries, what the query results should be, so we could do that completely end-to-end in an automated fashion. So to conclude, did we meet our goals? Well, we wanted to be realistic, and to do that, we modeled our data and our queries on a very important real-world use case, which is DevOps. And the simulation approach we used, combined with the telegraph metric modeling, we created data that was fairly plausible for somebody administering a server fleet or a fleet of containers. We were rigorous, and best indicator of that is that our system for both databases is end-to-end correct, in that the values that the queries produce are identical. Of course, it's reproducible with the random seeds and the other one other configuration variable that we call the scaling variable. These data sets and query sets are reproducible. All the code's open, it's online. Again, please take a look at it, submit any PRs or issues if you have any suggestions or concerns. And of course, we are competing with these other database systems. It's important to do these benchmarks in a good faith way. So it was very important to us that we represent our competitors in the best light, and we put a lot of effort into making Cassandra as performant as we knew how during this benchmark. So thank you very much. I appreciate your time, and I'm happy to take questions.
Great, Robert. So if you want to go ahead and pass me the ball, I'll jam through the last 3 slides, which are the actual results that we saw.
There you go.
Perfect. So yes, if you have any questions, now's the time to ask them in the Q&A. So there's basically 3 main categories or benchmarking results that came from the exercise. So if you haven't seen these, you probably did, whether it be in the blog post or in some tweet or something. But to recap, on write performance, InfluxDB was up to 4.5 times better than Cassandra. So higher is better in this particular chart as far as write throughput is concerned. as far as query performance is concerned, so here we're talking about query throughput, InfluxDB was up to 168 times better than Cassandra, right? And you can see the level of concurrencies along the bottom axis there. And then on-disk compression, meaning the on-disk storage requirements that you would have to account for, you can see that InfluxDB was up to 10.8 times better than Cassandra. So hopefully you can appreciate the exactness of some of these results, meaning that, as you can see through Robert's presentation, we were very rigorous in how we conducted the benchmarks, and we wanted to be absolutely fair so that anyone who is familiar with Cassandra, these would make sense, but then also that these are incredibly reproducible, meaning that you can take the benchmark suite and you can basically prove these points out for yourself. So again, these results are available in the companion technical paper that goes along with this presentation. I've gone ahead and put the URL in the chat window where you can download the paper to get these results. And then obviously you can go to the GitHub repo to download the benchmarking suite and run these yourself.